And now let's move, or let's continue with equilibrium constant in terms of partial pressure. For example, if the question asks us to express K, K is a constant, the constant for gas phase reaction in terms of partial pressure. So given this question, given this reaction of the formulation of ammonia from nitrogen and hydrogen. So first we need to see the coefficient of each species here. So the coefficient of this one is 1. So to find it again, we have the coefficient K is the idea is a product of a reactant, and here in this case it should be a partial pressure of our product. Here we have ammonia as our product, partial pressure of our product ammonia square, because we have two more here, because this is our coefficient, divide by partial pressure of the reactant. So here we do have N2, the coefficient is 1, so that's why partial pressure of nitrogen gas is equal to 1, and partial pressure of hydrogen gas is equal to power of 3. So because the coefficient of hydrogen gas here is 3, so here how we get it. So again, we have our general equation, K equal to coefficient of product over reactant, and it depends on the value of our partial pressure, the value of pressure, and don't forget about the coefficient. So again, this question asks us about consider the synthesis of ammonia and H3 at 298 Kelvin. Calculate the temperature of the solution at 298 Kelvin for a reaction mixture that consists of 1.0 atm nitrogen, 3.0 atm of hydrogen gas, and 0.5 atm of ammonia. So first thing first, what we need to do once we have this kind of equation, we need to write the chemical equation first, so it's easier for us to see what is what, or what is species, what is chemical reaction, and what are we dealing about. And next, because the question asks us about the delta Rg, so here we have our equation, delta Rg equal to delta Rg naught plus Rt ln Q. So first thing first, it's easier for us if we can calculate this ln Q first. So what I did here is, we know this one is pressure, consists of pressure. So again, ln Q is product over reactant. Here is our product, ammonia is product, and reactant is hydrogen, and nitrogen is our reactant. So for the gas, for the product, here is, we have this one. So the value, we have the value of each gas or each component in our system. So now our ammonia is 0.5 square, divided by our hydrogen gas is 3.0 atm, so 3 power of 3, because this is our coefficient. Remember this one that I said before. And our nitrogen gas is 1, so 1 power of 1, so we have a 9.26 10 power of 3. Sorry, we should have minus here. So here we should have minus. It's not Q. And then we put everything in our formula. We set everything in our formula. So here delta Rg naught give 33.3 kJ per mole. Plus, okay, again, here is the gas constant. So you need to know how to use how to use the value, either this one or this one. So it's depend on the dimension that we want to use. So now if we want to use this one, this is the dimension, so we need to use this value. So I hope you already know how to convert this value to this value, how to convert to 8.3145 to 0.083145. So hopefully, I wish that you already know how to convert this one. So that's why I already have, that's why I use this value, because I want to make the dimension is the same. So now 0.008345 kilojoule per mole per Kelvin times with the R is the temperature. Sorry, R is the remote constant, T is our temperature, and again we need to make sure our temperature must be in Kelvin because of the dimension, and then ln Q, so we already calculate this one, so just put it here. So and then our final equation will be that gives energy of the reaction equal to negative 44.9 kilojoule per mole. Okay, how about if we have this reaction? How about if we have to calculate equilibrium constant in terms of concentration? So what we do need to do is represent K for gas phase reaction in terms of concentration rather than partial pressure. So we use the same. It's slightly we need to change a little bit slightly our equation. So before we have a K equal to a partial pressure of a product over the reactant. So now what we need to do is we need to modify it a little bit. So we have K equal to Kc times with T over here is the vector 12.027 K. T is our temperature in the bracket. So here is delta V gas. Power of delta V gas. What is mean by delta V gas? Delta V gas is the differences in stoichiometric coefficient of a gas phase product minus reactant. So you remember it's only apply for gas phase. So for here, and given if we have this equation, the production of ammonia, the gas phase product minus reactant. So now we have 2 mole of ammonia. So that's why we write is 2 minus 1 mole of nitrogen, 1 plus 3 mole of hydrogen. So that's why we have the negative 2. So here how we determine the stoichiometric coefficient of the gas. In this case is the production of ammonia. So I will give you the example how to do this one. So for example, okay, how to write this one? Okay, I think we can do it together. From the above fraction, calculate the value of Kc. So again, we can use the formula of this one. So K equal to Kc plus T over 0.27. And here is our formula, T delta V gas. So what we need to do is the question asks us to find the Kc. So okay, we have K here is 5.8 times 10 power 5 equal to Kc. Now, should I find this Kc? Okay, T. For temperature now here is 298 Kelvin divided by 12.027. So here we need to remember that because the dimension of this one is Kelvin, so that's why we need to convert it to Kelvin. If we get the education as or the education give us temperature in degree centigrade unit, so we need to convert it to Kelvin, and delta V here is equal to the -2 because of delta V equal to product over reactant. So we need to know the coefficient of each of these ones. So our product is 2 minus this one is +1, and this one is +3. This one is 3, so +3. So that's why we have 2 minus 4. That's why we have -2. So we have this one. So you calculate this one first and move it to our left hand side. So our Kc, the value Kc is will be 3.6 10 to the power of 8. So I hope you can get this answer.